So in the second of these thermodynamics videos, we're going to look at the other key enthalpy changes that we need to be able to write equations for and identify from equations. So I mentioned at the end of the last video that the reason we're going to need a lot of enthalpy changes is because we're going to put them together in order to calculate the one that we've been talking about, lattice enthalpy. So lattice enthalpy cannot be directly determined, and so we're going to use a number of other enthalpy changes and Hess's law together to determine lattice enthalpy, and putting that all together is called a Born Haber cycle. So the type of cycle using Hess's law we're going to be using is called a Born Haber cycle. So we're going to go through a series of definitions. We're going to pay particular attention to what the 1 mole refers to, and then we're going to write equations and deal with them over the next few pages and in this little video. So our first one, standard enthalpy of formation, is one that we came across in the pack last year, the energetics pack. Standard enthalpy of formation. So what is the 1 mole about? That's our key every time. Here, it's the enthalpy change when 1 mole of a compound, so it's 1 mole of a compound, that's really important, we don't change the number of moles of the compound, is formed. So if the compound is formed, then the compound will be on the right hand side because we're making it from its elements. So on the left hand side we're going to have elements with their standard state symbols the way that we would have written them in the introduction pack. So is that element a metallic element just going around on its own? Is that element something like hydrogen, which we know is a diatomic element? And do we know the state symbols for all the elements? If you don't, it might be worth going back to the introduction to chemistry and just checking you remember the state symbols for the elements. So I want you to pause the video and see if you can give an equation to represent the standard enthalpy, so the enthalpy change when 1 mole of potassium chloride is formed from its elements this time. When we were doing lattice, it was from ions, but now we're doing just regular enthalpy of formation. It's going to be from its elements. Now this isn't the final answer, but this is just to talk through where I've got so far. I formed 1 mole of the compound, potassium chloride, and salts in their standard state are solids, and I've made it from the elements potassium, which is K, symbol K, and chlorine. Now the element chlorine is a diatomic element, so a Cl2 gas. Now I need to balance my equation, but I have to be careful because the definition says 1 mole of the compound, so I cannot change the number of KCl's. I can only change the number of K's and Cl2's on the left hand side. 1 K on each side already, but to get 1 Cl for KCl, I'm going to need a half a mole of Cl2. So it's really important that we get that number right. We cannot change the KCl's, we have to change the Cl2's. Now we need to decide whether this is always going to be a positive enthalpy change or a negative enthalpy change. And because it's formation, forming attractions is releasing energy. And if you're releasing energy, then it's going to be negative, it's going to be exothermic. So if you forget that exothermic and negative, it might be worth giving yourself a little note. So that's our first definition, and we've come across that one before. So our second definition is going to be the standard enthalpy of atomization. Okay, so the standard enthalpy of atomization. So again, we're going to concern ourselves mostly with what the 1 mole is about. So the enthalpy change when 1 mole of gaseous atoms formed. Now if they're formed, they're on the right hand side. So on the right hand side I'm going to have gaseous atoms. So just the symbol off the periodic table with a gas state symbol. And I'm forming it from the element. So on the left hand side I'm going to have the element in its standard state. So 1 mole of gaseous atoms on the right, the element in its standard state on the left. So any balancing will have to happen on the left. So pause the video and see if you can do these two, so for sodium and then for chlorine. Okay, so there we've got it. We've got sodium, 1 mole of sodium gaseous atoms formed from 1 mole, in this case, of sodium in its standard state, which is Na solid. What we're actually going to be doing in that process there is turning sodium solid into sodium gas. We're going to be breaking all the metallic bonds that hold that sodium in its lattice and turn it into gaseous atoms. And in this equation at the bottom, we had to have half a mole of chlorine gas, because that's the standard element Cl2 gas. We had to have half a mole to make 1 mole of chlorine gas atoms. And here we'll be breaking the actual covalent bond that holds 2 chlorine atoms together in order to have chlorine atoms free to move on their own. So we're breaking bonds in these reactions. And therefore, this is always going to be positive endothermic, because we need to put energy in to break those bonds and separate those atoms. So atomization is about making 1 mole of gaseous atoms. The only way the atoms can be free is if they're gases, because then they can move around, they're separated completely from whatever was holding them in some sort of structure. So even though chlorine molecules are moving around in Cl2 gas, until we break the bonds, we haven't got atoms free. Okay, so our next definition is called bond enthalpy. Bond enthalpy can be used in place of atomization sometimes, but not all the time. It can be used in place of atomization where the thing that we're trying to atomize is already a gas in its standard state as an element. Then we could swap it out for bond enthalpy. But the definition is slightly different. We've done this definition before. 1 mole of a given bond is broken in the gaseous state. So if we were going to do that, we could do that for chlorine. So we've got the Cl-Cl bond, and if we broke that in the gaseous state, because chlorine is a gas, then we could get 2 Cl gas atoms. Now, what you'll notice, if you flick back to the previous page, that equation looks quite similar to the atomization equation, but different as well. So how is it the same and how is it different? So when could I have swapped out bond enthalpy for atomization, but how would it be different? There you go. When I've had a look back, I noticed that this equation for bond enthalpy is twice the value of the enthalpy of atomization. It's 2 of everything, so it would be twice the number as well. It will still always be positive because we are still trying to break bonds, and not everything can have a bond enthalpy, whereas it could have an atomization. So you couldn't do a bond enthalpy for sodium, for example, because it doesn't have covalent bonds and it isn't a gas at room temperature. So sometimes you might see bond enthalpy used where another time you would see atomization, but not all the time. Atomization is our key term, bond enthalpy is just an extra little term that we might come across. First ionization energy we met last year in atomic structure. So our first ionization energy, what's the 1 mole about here? So here we've got the energy needed to remove 1 mole of electrons from 1 mole of atoms. So on the left we're going to have 1 mole of atoms, and on the right we're going to have 1 mole of electrons, and whatever else will be left over, and we need to know that we're doing it in the gaseous state. So again, pause the video and attempt to write the equation for 1 mole of lithium atoms losing a mole of electrons in the gaseous state. There we go. Lithium atoms on the left become lithium ions, all in the gaseous state, by losing 1 mole of electrons. That will always be positive because it takes energy to overcome the attraction between the nucleus and the electron. I've got to pull that electron off. What about second ionization energy? So what's the second ionization energy? So we're now looking at when 1 mole of gaseous 2 plus ions are formed, so they're going to be on the right, from 1 mole of gaseous 1 plus ions, which will be on the left. So yet again, pause the video and see if you can put that definition in words into a balanced chemical equation for calcium. So 1 mole of gaseous 1 plus ions becomes 1 mole of gaseous 2 plus ions by losing a mole of electrons. And again, it's going to take energy to pull that electron off. The value for second ionization energy will be bigger than the one for first. Why? Why would it take more energy to remove the second electron than it did the first electron? Have a think about that, pause the video. You could think back to when we went through this in atomic structure. So we talked about this in atomic structure. Once that first electron's been removed, the ion is now positive, so we've got more protons and electrons, and therefore we've got a stronger attraction between the nucleus and the electron being removed. We're trying to remove from a positive ion, so we've got that added attraction there that we have to overcome, so more energy is needed. So we've come across ionization energy before. That was about making positive ions. In this pack, we also need to know a way to make negative ions, and the way to make negative ions is something called electron affinity. If you have an affinity for something, you like it. We have an affinity for chocolate, then we like chocolate. So a liking or dragging in of electrons is called the first electron affinity. So we've got first electron affinity. And what's the 1 mole about? Remember, that's the key thing to try to get into your head. You have to change when 1 mole of 1 minus ions are formed, so they're going to be on the right, from 1 mole of gaseous atoms. So rather than ionization energy, which was removing the electrons, we're now adding the electrons to make negative ions. So write an equation to represent the first electron affinity of chlorine. So 1 mole of gaseous 1 minus ions are formed from 1 mole of gaseous atoms. And to get from there to there, we would need to add a mole of electrons. So the nucleus has got protons in it. At the moment it's sitting there, it's neutral, but the protons in the nucleus will still be attracting the electrons. So we're attracting, and anything that is an attraction releases energy, so is exothermic, a negative enthalpy change. This is a negative one. So similarly, we're going to look at a second electron affinity, and you can pause the video in a second and have a go at writing these equations. So the 1 mole of gaseous 2 minus ions formed from 1 mole of 1 minus ions gaseous. So pause the video and see if you can write that for oxygen. There we go. O minus gas plus electrons becomes O2 minus gas. 1 mole of gaseous 2 minus ions from 1 mole of gaseous 1 minus. We'll be doing this for anything in group 6 that needs to get to a 2 minus ion. This question now is probably one that we want to put a little star by. The exam board do love to ask this little section here. Second electron affinity is always, so all the others we've been saying positive or negative, exo or endothermic. Second electron affinity is always, and students are likely to say exo, just like first, but it's actually endothermic. So why would second electron affinity be positive when first electron affinity has been negative? So just have a little think, why would it take energy to put that second electron on? And we need to say to ourselves, well, the reason it takes energy is because I've got a negative ion and a negative electron. So as they come close to each other, they're going to repel. And in order to get them to come together, I've got to overcome the repulsion between the negative ion and the negative electron. So we would need to say energy is needed to overcome the repulsion between negative ions and negative electrons. And that is a really common question on the exam. So that's the end of the introduction of all these definitions. What we'll be moving on to in the next few pages is trying to put all these definitions together into a cycle.